we use the concept of variance and, thank you, standard deviation. Okay. Do you want to do the lecture? And with these two things, it allows us how much the data are spread out. And the concept is, in principle, quite easy. So let's say we have a set of data, let's say 10, 12, and 14. It's a very small set of data. And can you quickly calculate the mean for that, please? Loud? 12. It's 12, thank you. So the mean, let's say this is a sample. And we talked about the difference between sample and population the last time. Sample is just a sample of a larger population, if you like. So here the mean for this sample, how do you write this mean for a sample? What would be the symbol? It's an X bar, exactly. X bar is, I sum up all of them and divide by 3. So this would be 10 plus 12 plus 14 divided by 3, and that gives me 36 divided by 3, and the mean would be 12. And now to check out how far they are spread out, what I can do is for each data point, I can measure the distance between the data point and the mean. So if I depict it, we have 10 here, we've got 12 here, we've got 14 here, and I measure for each data point how far they are away from the mean. So the mean would be here. And for the first one, the difference would be, well, that would be 10 minus 12. So 10 minus 12. For the next one, it would be 12 minus 12. And for the third one, it would be 14 minus 12. Yeah? So this measures how far they are all away from the mean. So let's do that in the first place. 10 minus 12 is? Minus 2. 12 minus 12? 14 minus 12 is 2. So now when I go here, when I now look at that and say, okay, let's put them all together, I would get, if I put them together, I would get minus 2 plus 0 plus 2 would be 0. That's a bit daft, because 0 here in this case would tell me that the data are not in any way spread out. But they are spread out, aren't they? So I have to come up with a slightly different idea. And what we can do is, we can actually, if we want to take this approach, we can actually, instead of using the raw data like minus 2 and 2, we can actually square them. We can square all data, or the difference of all data, and that is a sort of, a dirty trick. It's a little bit like eye gouging in rugby. Good. Because whatever I square, it will always be positive. So what I would have here is I have 4 plus 0 plus 4. Which, of course, in this case, gives me 8. Yeah? So that is, this 8 is actually, if you like, the sum of the difference between data point, data, and mean squared. So I square the differences and add them together. And now, of course, I want to know what is my average. What's the average of this of these distances? Well, I had 3 data points. So I had, what was it, minus 2 squared plus 0 squared plus 2 squared, and that gives me 8. Now I want to know what is the average. And here it gets really nasty. So far, not a big problem. But now we get into the murky waters of population and sample. If we have a population, we use this number and say we know everything about a population, so we don't have to worry about anything, and we just simply divide by the number of data points in this population. So for the population, this would be 8 divided by 3, and that gives 2.67. Yeah? Happy with that? If we just have a sample, and we have an uncertainty in it. And it turned out that we can acknowledge this uncertainty by saying we have 8 divided by, and here it comes, n minus 1. So that would be 8 divided by 3 minus 1, which is 2, equals 8 divided by 2 equals 4. Now, our average difference from the mean, the squares from the mean, is different for a population compared to a sample. And this is because we don't know that much about a sample. We know far more about a population. Now this thing has a name, what we have done here. This is called actually the variance. So we can have the variance of a population or of a sample. And the variance for the sample will always be bigger than the variance for the population. And we can, in a way, if you like, what we can do is we can write this as this strange symbol, which means the sum of a data point, x minus x bar. This x, we can even give that an index. Don't worry too much about it. Squared. And for the population, we have n. And the same thing, x e minus x bar squared divided by n minus 1 if we have a sample. Okay? And we will do a little exercise in a minute for that. But people don't like this variance business terribly. And the reason is because there's a square in it. So the data that you have will always, the data that you have in here, will always be squared, which people don't really like. So they thought, actually, we have the variance here, but why don't we take just simply the square root of the whole thing? So, people said, we simply take the square root of the variance and that gives us a much nicer number. And this has been given the name of standard variation. So the standard variation is just simply, again, is a measure how far all the data are away from the mean. And what we can write is that as a general concept, standard deviation, that's this S, equals the square root of the variance when we talk about a sample, of the sample variance. So that's for a sample. Or we have this one here, that's the Greek sigma. This is the square root of the variance when we have a population. Is it both the same? No, because we know that the variance for the population is divided by n, whereas the variance for the sample is divided by n minus 1. So both variances are different, and therefore the square roots, the standard deviations, are different. Why don't we just simply do a quick calculation, a quick example for both? Let's say, bless you, I have the data point 20, 22, 24, 26. Now what I want you to do is, first of all, treat this as a population. So half of you, this half here, treats that as a population, and this half treats that as a sample. Yeah? So what I want you to do is calculate the mean, calculate the variance, and calculate the standard deviation. And I just abbreviate it like that. Okay? You will find very often the symbol sigma n or s square n minus 1. This n refers to whether we are dealing with a population or whether we are dealing with a sample here. Okay? If you don't have it, don't worry. You will be able to do these calculations quite easily in your head. Let's do another one, okay? Just for practice. We have the numbers 3, 5, 7, and 9. Population, sample, and I want to know what is the standard deviation. So the standard deviation here, and what is the standard deviation for the sample. Over to you guys. Have a go. Apparently it was a bad example because it's the same numbers as before. But what is the mean? The mean is in both cases 6. So we can calculate our variance, or we do the square of the square of differences. So we have 3 minus 6 squared plus 5 minus 6 squared plus 7 minus 6 squared plus 9 minus 6 squared. This gives us minus 3 squared plus minus 1 squared plus 1 squared plus 3 squared, 9 plus 1 plus 1 plus 9, and that gives us 20. So for the population, and the sample, we have for the variance, we have 20 divided by, and we had 4 data points. Whereas for the sample, we had 20 divided by 4 minus 1, which is 3. So here we get the variance of 5, and here 6.667. And now we can do the standard deviation equals the square root of the variance. And here the same. And we get square root of 5 and square root of 6.67, whatever. And we got 2.24. And here we have 2.58. Yeah? So we can record our findings, and we can say our x bar for this data point is 6 plus minus. What I'm going to do now, shall I take the standard deviation for sample or population, the way I have written it? Sample. Why sample? You're absolutely correct, but why sample? Because of the x bar. Exactly. X bar indicates it's a sample. Yeah? So that would be plus minus 2.58, and that is the standard deviation. Yeah? I could record that like this. Okay? Happy with that? Can you do that?